Okay, guys, we're going to start. So it's my pleasure to present here Marcos. Marcos Treviso has been working here for a while with Andre. This is PhD on the area of sparse attention, and now he's a professor here at Técnico, and he's doing a lot of very relevant work in the area of attention, in particular sparse attention, flash sparse attention, and we're very much looking forward to his talk.
All right, thanks, Kamal, for the introduction. So yeah, we're going to talk today about dynamic sparse attention at scale. So trying to make sparse attention really fast and more useful, okay? Just to contextualize, 9 years ago, I just looked at some photos. I was here at Alex Melas. I think you can see some people, can see Fernando, you can see André over there, right? So it's cool. And I remember this talk by Show, which was 9 years ago as well. It was before the Transformers era, and it was basically a talk about attention at that time. So it's fun how these things cycle. So as you probably know, so this talk was originally for Ivan Titov. He was going to talk about post-training for reasoning in LLMs. I'm going to give a different talk, but they share the same bottleneck, okay? Which is that usually in reasoning, they usually are made of long chains of thought, right? So LLMs can think for minutes, maybe some hours before answering. Usually nowadays they call tools, and these tools have really huge traces. And when you are talking to LLM, you usually have multiple conversations, multiple sessions, right? So these long sessions, they stack up and create a very, very long context. Curiously, in the last few days, I don't know if you saw this, but there was an employer from Anthropic that discovered a counterexample to a 87-year-old math problem, which was the Jacobian conjecture. And this, of course, was made with Claude Fable, which very likely used a lot of reasoning in the process. And what is more interesting, I think, is that Terence Tao, he created a blog post, he wrote a blog post on trying to digest this exactly solution. And if you go to the blog post, it's hard to understand everything that he's talking about, but it's interesting that at the end he says that he used an AI chatbot. So he used the GPT to try to understand everything in the conversation. And he shared the conversation. So the conversation is public. So you can see how exactly he interacts with GPT, which is quite nice. And I took the conversation, I computed some numbers. It was on average 10 to 20 minutes of thinking per each hard question that Terence was doing. The chat was so long that my browser actually lagged. And after some point, he actually activated Pro. So he said, oh, now I'm going to activate Pro, so think even more, which is fun. Then I computed some numbers with this tick token, which is the tokenizer for GPT. And it was in total something like 3 million tokens that was used in his chat. So this is a long, very long conversation. Right? So if you think about it, if you want something that is frontier reasoning, you are going to lead with something that is extremely long inputs and also extremely long generations. Right? So this is the bottleneck. So reasoning is bottlenecked by long context. And since we are using transformers, long context is bottlenecked by attention. Right? So maybe you can discuss a little bit more about what is attention. Right? Of course, these models, they have many capabilities, not just like using for mathematical discovery. They are used, for instance, for like writing an entire novel or for biological uses, for agents, now used a lot. So all of these applications, they generate huge contexts. Here is a plot showing the increase of model size, number of parameters, according to the years, right? You can see that like in the beginning, the models were not huge, even not billions. Then they started to gain traction. And around after 2022, something really happened, which is that ChatGPT was released, right? And this is where kind of started or kickstarted a lot of the large language models era. So models start to get even bigger in terms of parameters. So they start to get trained on chat data, so you could talk to the model more freely. You got new models like Llama, Gemini, Cloud, and all of them are based on these next token prediction laws. And as I said, they scale now to trillions of parameters. Here's a plot showing the like how the MMLU scores, so how accurate are these models, how good they are as a function of time. You can see that usually they are increasing. Right? You can see here that on the original ChatGPT was more or less here. So the models are not also increasing in size. You can see the bubbles increasing, so increasing the size of the models, but they also get more competent. Right? They get better. So to understand attention, I think Andrea already covered the transformers here as a lecture, right? So feel free to take to look at the lecture at YouTube. But usually when you're looking inside the transformers, there are these transformer blocks. Inside these blocks, there is this thing called multi-head attention module, right? This is the module that is important for long context. And we are going to understand why. So if you look at the self-attention block, it usually consists of basically three values interacting with each other: queries, keys, and values, right? We compute some scores as basically doing a dot product between all queries and all keys, right? This generates a square matrix. We pass it through a softmax function, so we get normalized probabilities across each row of this matrix. And then you do a convex combination with my values, right? So these are the three main steps of computing attention. In code, this looks like this in PyTorch. Really simple. A matmul, softmax, and another matmul. Right? So where is the bottleneck? I have to ask you, like, just or your intuition, or what do you think? Where is the bottleneck here in these three lines? Anyone? Matmul, which one? You have to have a matmul here and another one here. Yeah. The softmax. Why the softmax? That's also a bottleneck, so yes. That's also one bottleneck. Yeah. So basically, the major bottleneck here is materializing this matrix here, right? So this matrix is quadratic, the size of the sequence, n by n. Right? This is a very, very big matrix. Right? So you can see here in this plot the context length, so this n term here, as a function of time for the most popular models out there. You can see here that like GPT-3, which was like published in 2020, it was around 2K context length. It accepts 2K tokens. Nowadays, having something 2K tokens is a big no, right? Nobody will use a model with 2K tokens. Right? So we are going to see what made this thing blow up. We are going to understand why this was possible. Right? So something happened around 2022 that made models capable of handling much longer sequences. So yeah, as you probably know, if you want to train a LLM, scaling them like to billions of parameters or billions of context tokens is very challenging, right? So you take out like a huge chunk of the internet, use like 6,000 GPUs for 12 days, and you get at the end of like a 140 gigabyte file, right? But this costs around 2 million. So when you're doing stuff like this for a single training run, let's say everything goes well, nothing breaks, right? You don't do any hyperparameter search, it's going to cost you 2 million. Right? So you need to be really careful with what you're doing in terms of the attention mechanism. Because if that's going to be your bottleneck, that's where the cost is going to be attached to. Okay. So as I said, the complexity, the challenge here is the complexity of this big matrix, the n square, right? It takes n square memory. Right? So just to store this matrix into a GPU, for instance, it takes n squared. This is huge, okay? So let's focus on only the training complexity. So just a back of note calculation here. Like if you have just one sample, just one sequence in your batch, you are training a model, right? It uses 4K tokens, using a standard transformer with 16 heads in 32 flat precision. Just this single sample, just this sample, one layer, 16 heads is going to cost you 1 gigabyte of your GPU. So this is a lot. Nobody's going to use one sample, right? So if you start playing with this number with N or B, you very quickly run out of GPU memory. You cannot train your model. So here's a curious some curious numbers. So texts usually, depending where you go, if you go to code base, they can be more, books can be more, but it's usually in the range of thousands. Okay. If you start going to audio, you start getting to millions. Videos are even bigger, right? In agents, they are kind of unbounded. They keep generating. The context is basically the working memory of the agent. So they will keep generating as long as you go. Okay. So if you want models that truly handle long context, they will need some kind of efficient attention to deal with this bottleneck. And before LLMs, attention heads were sparse. So there were a lot of papers looking at attention heads and plotting these attention maps. And you could see visually that a lot of them, they were just focusing on a few words, right? Or a few columns. So a lot of the computation seemed unnecessary, but they were still doing all the computation nevertheless. Okay. So just a quick poll before we proceed. So let's say I take a Llama 8 billion models, and it reads a 128K token prompt. So what fraction of the attention score, the score entries, is enough to capture 96% of all attention mass? Right? So how many tokens usually I have to have in proportion to the total number of tokens so that I capture almost all attention mass probability? Who thinks is A? Raise your hand. B? Raise your hand. 1. C? And D? Okay, it's among D and C. The correct answer is C. Okay, so there's this paper looking at efficient ways of basically serving LLMs, and they basically saw that a lot of these attention maps are super sparse, so you can just basically focus on the first tokens and the diagonal, and you are good enough for most applications. Okay, so we already have this knowledge that attention maps are quite sparse, but we still use something like softmax that is truly dense. Anyway, so back in 2020, there was a taxonomy created by Tayarao. They did a survey paper, serving a lot of approaches for efficient transformers. And there were a lot of approaches here. They discovered a lot of approaches. But turns out not all of them were used at the time, right? It's just they were there, they were interesting, but people were not using them. So it's interesting to pay a little bit attention to what kind of patterns or what kind of sparse attention they were investigating, so we can differentiate a bit from that. So they identified basically 2 key types of attention, right? One were basically fixed patterns. So think about having a sliding window. Other words like global. So I would always focus on the first tokens of my input. Others were like random. Somehow that worked. So we can say that like this has low adaptivity because I'm always focusing on the things that I defined a priori, right? It has low flexibility as well because I have to basically decide whether it's going to be 2 or 3 or 4 tokens, but never beyond that. But it's full differentiable. I can train a model with this very easy. And turns out this is very fast because I only need to attend to a very specific limited number of tokens. Another category was dynamic selection. So things that include like doing top K or LSH or clustering before doing attention. Okay. So this is more adaptive. It's a little bit more flexible because now I can tune this K a little bit, but it's basically not differentiable. Okay. It's very hard to train with backpropagation. Or it are going to lead you to some instabilities. And it's at least faster than doing n square. Okay. But as I said, they are not very used in practice because all of these methods, including new ones like in the NSA, MOBA, they kind of trade accuracy, the model performance, with efficiency. Okay, this is exactly the problem that people in 2022 were trying to avoid. Okay, so as I said before, I had this nice picture. This was GPT-3. There was something that happened over here that changed this view, which was the introduction of flash attention, right? So flash attention was kind of a revolution here in the field because after flash attention, the context size of models grew exponentially. Okay, so it's interesting to see what exactly flash attention did to achieve that. Why is flash attention different? right? So flash attention, what they did is that they created a hardware-aware implementation of softmax attention. So I have softmax, I will go with softmax, I know that it's dense, but I'm going to make it very efficient at GPUs. And the way they did this is by following this memory hierarchy in GPUs. We have something like the main memory in your computer, like DRAM, right? Then I have GPU memory, like HBM, which is the first memory that you see when you're working with GPU is this memory here, HBM. And then you have the fast memory where things get computed, right? The problem is that fast memory, as usually in computer science, fast memories, they have less capacity, okay? So you need to be very smart in the way they use this memory hierarchy. So before we had something like this, right? I said the bottleneck, one of the bottlenecks was in materializing this matrix. So if you go implement this in PyTorch, what PyTorch is going to do is something like this. It will load queries and keys from HBM, this low memory here from the GPU. It's going to compute the matmul in the fast memory. That's nice. But then it's going to store the result back into HBM. If I proceed, then I'm going to load Z from HBM, which was just stored. I'm going to compute softmax in my fast memory, and then I'm going to store P again. And finally, I'm going to load P in V. I'm going to compute the matmul, and then I'm going to store the output in this low memory. What flash attention does is do everything in one pass. You load your keys and your values from HBM. You compute Z and P in SRAM, and in the end, you store your matrix O. Okay. So there are some key things in flash attention that they were basically responsible for allowing this to happen. The first one was tiling. If you don't do tiling, you will need to load basically entire matrix. What they do instead is that they load a few blocks. Let's say I have keys here, I have keys over there. I load one block of keys, one block of keys. I compute their matmul, right? I compute some partial probability here. It's called online softmax. I multiply with V, which is my value vectors, and I start this in an output. Okay, so all of this is done in a single loop. I never store things into HBM and then I read them again. No, I only use fast memory for these intermediate steps. Okay. But you may ask, okay, this is cool. I'm going to apply this in my forward pass, but how am I going to back propagate through this? Like now I have a huge GPU kernel here in the forward pass. If I use PyTorch, how am I going to train this model with this thing? Right. So what they did is basically the same trick. So for the backward pass, they have a flash attention for the backward pass. So you have a kernel for the forward and a custom kernel for the backward. Okay. The results that they got were really, really good at the time. So they got, for instance, a huge reduction in time in flash attention, but also a huge reduction in memory, something like 20 times reduction compared with other methods, with just materializing the matrix. Okay. And something that is important overall this is that the method is fully exact. It doesn't do any kind of approximation. Okay. So if you want your model to be as performant as it was before, but you just want to be faster, you don't need to use like some kind of approximation or linear attention, whatever. You just replace with flash attention. It's going to be the exact same model, but faster. Okay. This was basically what allowed that big curve to happen. Okay. This is what allowed this exponential growth. So now I have something that is very fast. It doesn't have the quadratic memory bottleneck. Okay. So I can start scaling things. Yeah, but can we just keep increasing the context? So now we are in the range of like 1 million context size or 10 million context size. Can we just keep increasing? Let's say, let's go to infinite context. Can we do that with flash attention? Right? In practice, you could, like nothing forbids you, like in terms of memory, as long as you have enough linear memory, you could do it. But there are some issues here, right? There was a paper in 2024 that they were analyzing how information flows inside transformers, especially with softmax. And there is this problem that happens that it's called representational collapse, which means that as you keep adding ones to your sequence, this is just a sequence of ones, right? You get a representation in the end, the first layer here. after L layers. Sorry. You get a representation. If you add another one to your input, you get this. And then you start getting vectors that are more similar and more similar to each other. In the end, as you add a bunch of ones, you're kind of converging to a fixed representation, a fixed vector. And that's going to be the vector of your sequence of ones, regardless of how many ones you have. It can be 1 million, it can be 1 trillion. It's going to be the same vector. This is terrible because it means that my model cannot differentiate between something that is 1 million tokens and 1 trillion tokens. Right? Here is another problem they saw. It's called overview question. So here, a lot of information from context tokens is forced through a single fixed size bottleneck. You can see that all connections here, they are forced to go out into predicting this token Y5. Okay. So this creates a lot of information that gets squashed into a single neuron. Another problem is called attention dispersion. Right? In this problem, as you increase the number of tokens, the coefficients start to spread out. So attention starts to become very diffuse here, very dispersed. Right? So it's basically converged into a uniform distribution, which is just a simple average. Right? You're doing a simple average of your value vectors. You could just take your value vectors and calculate the mean and produce that as the output of your attention mechanism. Right? So what's going on? Why are these problems happening? Well, long story short, the problem here is softmax. Okay, the problem is that softmax has this expression. It uses the exponential divided by the sum of exponentials. Exponential is a function that always returns a positive number, right? And if you have something that n goes to infinity, you're going to divide by a lot of terms. They are never zero, right? So this denominator is going to dominate everything. This means that all computation paths in your graph are going to be active. So this is going to lead to overexpression. And all tokens are going to contribute somehow, even if it's just a tiny bit. So we are going to have something like representational collapse, right? So it doesn't matter how we start increasing this number of tokens, softmax is going to spread out the mass to everything. So in the end, you get something that is unfocused. You don't have a focus on the things that matter. It just spreads out. Okay? So to understand a possible fix, we need to understand what is softmax exactly. There is this geometric object called the probability simplex, right? Which means that is the set of vectors that are positive in sum to 1. Okay, are non-zero in sum to 1. So you can take in 2D as this line here. Like if I have 0.8, the other is going to be 0.2, etc. In 3D, I have something that looks like this triangle. Right? In larger dimensions, of course, you get something else. Like in 4D, you get a tetrahedron. Okay. So if you want to map a score to a probability, that's the whole point of doing attention. Like I want to do a weighted average of my value vectors. I want a way of mapping my scores, my Z, my square matrix, to probabilities, right? And if you think about this geometrically, this means that I have a point in space, a vector here, and I want to map onto the probability simplex. Okay. There are many ways of doing this. Like this is not new. Okay. If you just take the argmax function, you can represent the argmax points as basically the vertices of this simplex. Okay. So 0, 1, 0 is this point, 0, 0, 1 is this one, 1, 0, 0 is this one. Right? This is the extreme case. This is super sparse. This is the argmax. If I add an entropy regularizer, let's say I don't have any entropy, I recover argmax. If I have something like Shannon entropy, I recover softmax. So softmax is not just the exponential divided by the sum of exponentials. It's basically I'm mapping onto the probability simplex with a regularization term, an entropy regularization term. Okay. If I use a different entropy like Gini entropy, I get sparse max. And if I use something called Sally's entropy, which is this term here, you don't need to be scared by it. You get something that is in the middle, in between. So you get something that basically interpolates between softmax over here and argmax in the extreme case. So if it goes to 1, you recover softmax. If you go to infinite, it recovers argmax. In the middle, you have some nice terms. For example, alpha equals to 2, you get sparse max. But you can use other values of alpha. Okay. So alpha into max is one of these potential probability maps that we can use inside attention to get some sparsity, right? Because as we saw here, it maps to these boundaries of the simplex, right? And since it's the boundary, it means that the probability vector has some zeros in it, which means that it's sparse. In practice, the evaluation form of Ntmax looks like this. Okay, it's really easy to compute. It's just like a ReLU function. It's maximum between 0 and something, right? And what matters here, and then I put to a power. What matters here is this parameter tau, right? This is something that we don't know what it is yet. It's something basically that ensures that the final output sums to 1. Okay. For softmax, this is quite easy because this is going to be the log sum exp. Okay. But for other transformations, we need some way to find this parameter. Okay. And you're going to talk a little bit about how we can find this later in a very efficient way. But in contrast to softmax, if you had this drawing from before, if you keep increasing the context with Ntmax, you're going to get something that looks more or less like this for the same input, right? So with Ntmax, just by changing from softmax to Ntmax, I was able to maintain focus on the things that matter even at extreme long context. So yeah, this is interesting, but why complicate so much? Like if you want sparsity, like why not using something like top K, or I do ReLU, then I try to normalize ReLUs? This is maybe the first thing that we would do, right? And the reason for this is that, if you use top K, it's slow to evaluate. It requires basically sorting, right? It's not GPU friendly. There are many research on this, but it's not very GPU friendly. It's non-differentiable, so you have these huge discontinuities in the map. But it's controllable. You can tune this K if you want. Okay? Another option would be like normalizing ReLUs, but this is easy to evaluate in comparison to top K. It doesn't require any sorting. It's very friendly GPU-wise because it's just a limit-wise operation. It has some tricks in differentiability here because you can get 0 divided by 0, okay? But it's not controllable, so you cannot tune much stuff. Right? If you have something like Ntmax, for example, it's easy to evaluate. So it's just that formula with max 0 and something. It's GPU friendly, as we will see. For a long time it was not, but now it is. It's totally differentiable, or differentiable almost everywhere, and it's controllable because we can control this alpha parameter. Okay? So if you go back to those kinds of sparse attention that I showed you, here is what a sparse kind of attention that we have with Ntmax is a sparse distribution, right? So it's something that is highly adaptive because our sparsity is adapted with the input. You don't set a K like in top K a priori, you can go with that. It adapts the amount of zeros. It's very flexible, so you can change this alpha to control the distribution, and it's almost everywhere differentiable. But the problem is that, up to this point, it was very slow. It required sorting, it required a lot of other approaches. Okay, here is the actual algorithms for computing, for instance, sparse max and alpha into max with alpha equals to 1.5. Right? You don't need to worry about the algorithm itself, okay? But something that you need to take a look at is that the first operation is a sorting operation. Right? So if required to materialize my matrix Z, I do a sort operation. In the same thing here, I do a sort operation, right? So, and this is just for alpha equals to 2, alpha equals to 1.5. What if I want another value of alpha, like alpha 1.75? Then these two algorithms, they don't work, okay? So they don't work for our values of alpha, and they require sorting, which is not GPU friendly. So can we have something that is more like in the flash attention style or for Ntmax attention? And the answer is yes. This was a paper that I published with Nuno Gonçalves, which is a PhD student, and André, last year at ACML, where we proposed something that is adaptive sparse flash attention, ADSFlash for short. Okay. What we do in this in this paper is that we take the algorithm from computing attention, right? So this is just like, oh, I load keys, my queries, etc. I go to each of them, and I compute tau using something called Halley bisection. Then once I have this tau, I just apply sparse max, int max very easily, just element-wise operation. Okay. You probably don't know what is Halley bisection, right? So let me explain a little bit. So bisection is a very simple algorithm, right? I start at some point, I want to find the root. I want to find tau such that the entire expression, entire p sums to 1. So it's just one parameter. So I start with some value, I guess one random value. Then I see if it's if it's on the left or the right side of the root. If it's on the right, I close this gap, this limit. If it's on the left, I close the other one until I converge. Okay, so this is bisection. It's like a binary search. Okay, what we did in this paper is that we combined naive bisection, with Halley's method. So Halley's method is something like Newton's method by using second-order information to accelerate this step. So instead of jumping around the root a lot of times, we take like a few steps to be very close to the root. Okay, and this is very efficient to do in GPUs because all these operations, they are element-wise. Okay, it's just basically redoing these operations here, maximum of something, etc., and summing. That's all it takes. So they are very GPU friendly. The problem is that we will need to load keys a lot of times during this process. Okay. Yeah, but why we say that this is efficient at all? So if you look at this tiny matrix here, you can see that a lot of entries here are 0, right? So this means that our backward pass, my matrix, they also have these zeros, right? So this means that in the backward pass, I can just iterate over keys and keys that are non-zero, that lead to non-zero values. Okay. This allows us to skip a lot of computations in the backward pass. This is a low-hanging fruit since this Sparse Max paper from 2016, so it took a long time, 9 years, to make Sparse Max really efficient in practice. Right? In 2016, André and Camon over here, they said that the Jacobian, the backward pass, can be computing only the size of the support, the size of non-zeros. Right? So it took us around 9 years to fully make Sparse Max efficient. Here are some numbers for add splash. What is curious here, like you don't need to focus on all columns, right? I want to compare with just bisection, which is in PyTorch. This is the standard way of computing int max, and the versions with add splash, which are the purple ones. Right? You can see over here that after some point, the naive way of computing int max just breaks. You go out of memory because you need to materialize the entire matrix. You need to do sorting, etc. So you run out of memory. So you could not scale models with int max attention. Now you can, right? Now the values with data splash, they don't run out of memory. But not only that, it turns out that this first version of data splash, it was also faster than flash attention. Right? So flash attention, the thing that people have been using for, let's say, at least 40 years now, the thing that we built over here is even faster than flash attention. A few percent, just a tiny bit, but it's even faster than that. Okay. Then a few times later, we said, oh, maybe there are room for improvements. Then one of our students, Nuno, he came up with a new idea for making add splash even faster. Okay. So there were basically two main ideas. The first idea was basically the Halley bisection could diverge at some point, so we improved the optimization algorithm a bit. And the second was to basically have an initialization for finding this tau that was better, that was more close to the root. This means that when I'm going over all key blocks, I will only need to go over them a few times. Right? So I'm decreasing the number of times that I pass over keys. So this transfers between HBM, this low memory, to the fast memory, it was decreased. Okay. So the way that we did this is basically having a histogram in SRAM. This histogram is something really simple. It just counts how many scores, dot products between queries and keys. are below some threshold. And then I create this histogram inside the fast memory, right? And then I compute tau based on the histogram and not based on my Hill scores. And this is going to give me a lower bound on the real tau. Okay, so here's a plot on the number of iterations between to achieve the to be close to the root to converge. Right? So the standard bisection takes a lot of iterations, like 20 iterations. You can go over here there. Other splash one, which is this hybrid, it took like 3-4 iterations. But for other splash two, here I have a different number of bins in my histogram. You can see that even after one iteration, it already leads to an error term that is very small, 10 to the minus 8 or something. So with one iteration, we already converge. So this means that we can save a lot of computation by not loading keys all the time. So here is some plot of other splash one in comparison with flash attention. You can see here that it was required a lot of sparsity for us to actually beat flash attention, and this was just by a tiny bit. And now with other splash 2, we pull this margin a little bit up. Okay. Now we need much less sparsity to be more efficient than flash attention. Here's another plot showing for even longer sequences, like for instance for 128K, something like this with 85% sparsity. We are close to be something like 2 times faster than flash attention, which is huge. Okay. Some results in terms of like using sparse attention in real settings. This is a benchmark called Ruler. It's basically a benchmark to see how good is our model at long context, right? There are some, you don't need to look at all these numbers, like you look at the average, it's already good. But if you take a look at these columns here, they are very important for like agents, because these are common, for our text, like common words extraction is to extract like which words are more common in my input, to count how many words we have, and to keep track of variables, right? For these particular tasks over here, the jump between using something like softmax to entmax is huge. So the standard way of people do in LLMs using softmax with rope, almost all LLMs use this setting. You get something like 0% variable tracking accuracy, but entmax you get something like 27. So yeah, it's not perfect, but it's much, much better, right? So and you can improve these numbers by simply just scaling your model a bit. Okay. Here's another table of results. Here, what matters here is basically the average, okay? You can see that in comparison to the standard way for doing softmax plus rope, get some almost like 2 times the accuracy, okay, on these long tasks. And this particular benchmark is super relevant for RAG systems or for things that are like in context learning stuff, okay? So yeah, we train a model with Unsplash. So it's fast and it's really good at long context. Can we look at how sparse is the model? And this is a plot that shows basically how sparse is each head in each layer in the model, right? So the lighter it is the square here, more sparse is the model. So it turns out that for this particular example, it was around something like 95% sparsity. So in practice, the models are extremely sparse. And if you use something like flash attention or softmax, you're not leveraging this sparsity at all. You're just wasting all your computation comparing all tokens to all tokens. Yeah, so this is nice. So we have now a way of training entmax attention models in a very efficient way. But what happens with attention on sequences that are longer than those seen during training? So the usual way that we do long context with LLMs, it works like this. It works with the path of pain, okay? If you want your model to support 32K, you train on 32K, right? Then you say, oh, but now I want like my clients or whatever, they are asking for more context. They want to throw an entire book into GPT or something. So what you do, you need to train on 64K tokens. If you want to expand again, guess what? You need to train on 128K tokens and so far. So every time that you want to increase your context length, you need to train your model on that sequence length. An alternative, which I call the path of joy, is that you train on 32K and you have a method that generalizes well to longer sequences. So you don't need to train on very long sequence like 1 million, which is going to cost a lot. You just need to apply it. You run your model on this long sequence. Okay. This is what we study in this paper. So the full proofs and statements are in the paper. Feel free to look at there, but let me just give you the final results. So something that we noticed is, I don't know if you remember, this is a representational collapse that was saying in the beginning that vectors start to look more similar to each other as you added ones to the input. What happens with sparse attention is that this difference doesn't go to zero. It stabilizes. So this means that the model are not collapsing. It also alleviates over-squashing because now in the backward pass, you don't need to communicate all information across all tokens. Just some of them are active. Okay. And interestingly, we also saw that Intmax, not just theoretically, because theoretically it maintains focus, as we saw, but also in practice. Like this is a simple task. I think it was max retrieval. It's trying to retrieve the maximum in a sequence. And you can clearly see that softmax, after some point, after some tokens over here, the attention becomes dispersed. It looks black because all tokens receive the same attention. Whereas for Intmax, you get this nice diagonal. So only the tokens in the diagonal, which are close to the maximum, get this probability distribution. But yeah, so Intmax is good in this sense because it allows us to, to give the model some sparsity. But what if it gives too much sparsity? Right? What if it ignores too many tokens? So what we propose in this paper is having these scaling parameters here to counteract excessive sparsification. Right? And we define them as with learnable parameters in the model. So I made delta learnable, beta learnable, and gamma learnable. And I also use the sequence length as information to scale my logits. Okay? Something that we realized very early is that, not surprisingly, but every head in my model, they behave quite differently from each other. So some models learn to have like betas that were negative, others that were positive, gammas that were positive, others that were negative. So we really needed to make these parameters not also input dependent, but head dependent. Another thing that is important is all these models, as I said, they use rope, right? But turns out, after a lot of stress testing, that rope doesn't work really well with sparse attention. Like in the paper, you can take a look. There are like huge theoretical motivations for that. In practice, that means that if you're going to get rid of rope, you need some other kind of position encoding, right? So what we propose in this paper is something called NAPE, where half of the heads use no position encoding at all. In the other half of the heads use something like alibis, like a sliding window. Okay, and this combination is very strong, not just for Intmax, but also for softmax. Okay. Here are some results with this approach. You can see here for this multi-query token associative recall, so just a recall task with multiple queries, multiple keys, very hard problem. You can look at this dashed black curve. This is softmax with rope. Okay. As soon as you go out of the in distribution, so I trended on 32, I go to in 64.8 and I go to 128, the model just collapses. It cannot generalize. Okay. If you use something like AS Intmax, you can generalize to 1,000 context length. So you trained it on something like 64, and now you can apply it to 64,000. Okay. This is another task called max retrieval. We didn't even put softmax with rope here because it just collapsed even during training. Okay. But you can see again the AS Intmax maintains a much better extrapolation curve. So these are other results on language modeling. I'm not going to derail too much into this, but you can see here that on language modeling like archive papers or PubMed, having something like AS Intmax, it keeps your loss, your perplexity very small as you increase to longer context. Right? Whereas for something like softmax is not as good. Again, needle in the haystack, this one is interesting. Like this one is some results from our paper, exactly on this needle in the haystack kind of benchmark. If you compare with recent Mamba 3 paper, which came out like maybe 3 months ago, they were claiming like huge extrapolation results because they were able to extrapolate to 4K. Trained it on 2K, they extrapolate to 4K with 8.8. And if you look at our results, we extrapolate to 100 at the same setting. Okay. And if you go twice that, you still have 99% of accuracy. If you look at the linear haystack 2, it's also the same thing. Like for 4K, they have like 50% extrapolation accuracy, and we have something like 83, it's much higher. Okay. So this shows basically that there's something here that we are doing right. So there is something with sparse attention that allows us to generalize to longer inputs and to handle longer inputs very well during training. But a different problem is, what if you want to do inference? Right. So inference is a totally different systems problem. Right? During training, we have the forward pass, we have all of our tokens, we are compute bound if you use a GPU kernel. And you have the backward pass as well to compute, so you can optimize in a lot of places. But at inference time, during prefill, when you append the document and the model is computing attention for these given tokens, you are compute bound as well, but you don't have the backward pass. And during generation, when the model starts generating token, you are totally memory bound, okay? Because you can only generate one token at a time. So in our research, I have two ongoing directions on this. One is to use good approximations at decoding. So if I want to use Nmax, an Nmax model that we know that is very efficient for training and to handle long context as well, if I want to use in practice, something that we can do is using good approximations at decoding time to make it fast. Another solution is to break attention in a hierarchy. And I'm going to comment a little quick about these two directions. So the first one is collaboration with Gonçalo Duarte and Miguel Cossero here from Técnico. The way they work is basically if you take a look at softmax distribution, okay, and you apply top K, you are essentially always going to lose some probability mass by definition, unless your K is the size of the input. Okay. Whereas for Nmax, if you apply top K, and this K is higher than this support size, the number of tokens in case of non-zero, your final distribution is going to be exact. It's not going to be an approximation. Okay. So this gives us the motivation to try different approximation strategies for Nmax at inference time. So here is a plot showing how we do top K attention for softmax in the needle in the haystack problem. Okay. You can see that after some point, after some length, the models with softmax start to degrade a lot. Okay. The models cannot recover the needle anymore. Whereas for Nmax, you get something that looks almost 100% across the board. After some point, it goes down, okay? But it extrapolates much, much better. And this is using top K, okay? This is using top K Nmax, not just Nmax. So approximating Nmax, but in a way that it's better than approximating softmax. So these are some results in terms of wall clock time. We can see over here, like just at 1 million tokens, let's go extreme. At 1 million tokens, so I'm trying to decode 1 million tokens. If I use something that is proposed in this paper, which is like a Gaussian approximated version for Nmax, we get 3 times the speed up over softmax, over flash decoding, which is the standard from many ways of serving LLMs. If I use the top K version, the one that was the result from before, we still get some speed up, like 1.25. And there is still room for improvement in terms of like engineering these kernels, because we compare with things that are developed by NVIDIA, and these were basically developed by us. Right? Another line of work is dash attention, so using hierarchy. And here, what we do is we break attention into 3 stages. This is similar to NSA from DeepSeek. So in the first stage, we basically take a chunk of my input. So I take like a window of my input, and I aggregate all that with a learnable query. Okay, I have this learnable query, I aggregate this into a single chunk. Then I do attention over chunks using Nmax. Okay, some scores are going to be exactly 0. Right? And then I use these Nmax scores as priors for my next stage, which is going to open up these chunks, going to get the real vectors, and going to weight these vectors by the Nmax probabilities. Okay. So this gives us basically a way of combining entmax for efficiency and softmax for the last stage for doing a single pass. Okay. So this is not just efficient, it also deals well with the problem with long context. Here are some results in terms of the sparse accuracy trade-off. You can clearly see that if you compare with something like NSA from DeepSeek or InfLM, it has a better trade-off in terms of how increased sparsity, how your accuracy behaves. And finally, here are some results in terms of prefill in decoding in generation. You can see that like in the extremes case, like 93% sparsity, which is the case, by the way. As I said, like these heads in transformers, they are very, very sparse, like 95% sparse. We get around like 3 times speed up for both prefill and decoding. Okay. So just to finalize then, overall, this line of work, we kind of discovered a way of creating a method, a module, that is on par with softmax on small sequence. So if you go to small sequence benchmarks, it's on par, but it's better, much better on long context benchmarks. Okay. And just a disclaimer that all our implementation is doing something called Triton, which is embedded language. So it's not something that is very optimized like QtDSL, Qtile, or directly in CUDA. So there is much room for improvements here. Okay. And we are in academic budget. Okay, so we are not NVIDIA, we are not Google, we are not Anthropic. So we are trying to scale larger models with this. So results are coming. But just these models are in a small scale for now. But it's interesting that this direction of combining GPUs with dynamic sparsity, there are a lot of people interested in this direction because it works. Okay. Just recently, I think it was yesterday, NVIDIA just released this blog post on like revealing some things regarding the new GPU architecture, which is Vera Rubin. And they have a section just dedicated on adaptive compression sparsity, right? So GPUs, in the next version of GPUs, will be able to do adaptive compression sparsity by default. You don't even need to tweak your model to do that, okay? And yeah, that's it. Thank you for your attention. Do you have any questions?
Right. Thank you for your lecture. Thank you for your lecture. I was just wondering if you could once more explain why flash attention is linear and not quadratic.
Sure. Let me see if I can find the flash attention slide. It's going to be easier to explain. So, here. So basically the reason it's linear is that, attention, we say that it's quadratic because we materialize this matrix, right? So this Z matrix is n by n. Right? The way flash attention does is that it goes block by block of queries and keys, right? And it never materializes this matrix. Okay, so it only needs linear memory for doing these internal computations. Right? So think of, let's say you're going to implement this in PyTorch, right? Instead of computing the matmul between your queries in your keys, right? You do a for loop, right? Do a for loop and go row by row, right? That's it.
Okay, thank you.
While you're on the slide, can you also talk a little bit more about the subsequent versions of flash attention, like what they do on top of this, like flash attention 2, especially 3 and 4, because they're more architecture specific?
Yeah, so, I mean, I'm not an expert on flash attention, okay? But we compare a lot with flash attention 2 because, let me go back to this slide. Like flash attention 3, they do a lot of different things regarding the GPU itself. So they do like things like warp scheduling, warp specialization, and a bunch of other tricks that is not changing the algorithm itself. The algorithm is still doing something like in this figure. I load tiles of keys, tiles of queries, multiply them and use online softmax, okay, to compute the output. What changes in flash attention 3 is that you have like some things from the Hopper architecture in GPUs that is leveraged in flash attention 3, like warp specialization, TMAs. In flash attention 4, there are things in Blackwell in the newer GPUs that flash attention leverages. They also do some kind of approximation in flash attention 4, which is that instead of computing the exponential, because the exponential start to, just the function exponential, start to become a bottleneck in GPUs. So what they do is that they replace that by some polynomial, okay? And just to make it faster. And this is interesting because in the case of Nmax, we don't have exponentials, we just have a power, right? You can just like square it. And squaring in GPUs is very fast.
Thank you.
Hello. This is maybe a more Euro LLM question.
Mhm.
Are you guys already using any type of sparse max or Nmax in current Euro LLM? And if not, are the next versions going to try these techniques?
See, maybe André can talk more about that. We are trying. For now, I would say no, because there are a lot of engineering efforts that need to be taken care of. Like everything, there is this thing called the hardware lottery by Sarah Hooker. That is true. Right? A lot of things were optimized toward transformers with softmax attention. So there is a huge engineering work that needs to be done before applying Nmax to really, really big models.
But is it really on the GPU kernel side of things? GPUs are not ready to do this efficiently at large scale?
I mean, not just in the GPU side, but in terms of programming as well. Like there are a lot of tricks for training very big models that it needs to be different for Nmax. For example, if you want to do something that a model that doesn't fit in a single GPU, right? Which is the case when you're going to very big models. So you need some way of doing a parallelism across many GPUs, right? So this is a different way of computing Nmax. For softmax, they already have that. There are many optimizations, including from NVIDIA itself and many other collaborations. So for Nmax, there is nothing.
Okay, cool. Thank you.
We are working on that. Yeah.
Okay. No, mine was just I think it would be a quick question is, okay, the algorithm changes a lot, so it becomes faster, but did you do any studies on energy consumption, how it changes? Because some of the processes also change, and I want to understand a bit of the energy cost impact of this change.
I see. You mean like when we change from Ada Splash 1 to Ada Splash 2? Is that it? Well, to answer the question directly, no, we didn't. We didn't measure. But my suspicion is that it's going to decrease the number of like the energy consumption because now we are doing less iterations, right? So definitely going to decrease. Now, there are a lot of things that are more intricate. For example, if you are going to use newer generations of GPUs, there are some tricks that you can use that you cannot use in older GPUs. So I don't know how like using these different techniques impact the energy consumption. It might be the case that even after decreasing the number of steps, it might be using more energy because the resources used, like the methods used in GPU are like more expensive or something.
Thanks for the talk. I was wondering, since Ada Splash is dropping basically irrelevant tokens in a dynamic way, how these, I don't know if you investigated that, but how this helps with quantization, like having less, like fewer attention matrices, like smaller one.
Mm-hmm.
It does help with it.
Well, there are some. I was one student that has started working on this like from last month. And our previous results says that yes, it helps because when you try to quantize a value for softmax, let's say, and this value suddenly becomes like 0, right? You are throwing away information. But for intmax, for quantizing a value that afterwards it's going to be 0 and it was 0 anyway, you're not losing anything, right? So we are getting some positive results in that regard, but we need more work. But that's an interesting direction.
Thank you for the talk. It is really interesting to maybe put this on like edge devices and maybe browsers. I was wondering the trade-off between performance and the sparsity. Does the sparsity make it less performant, or isn't like the redundancy of the tokens good to performance? I was just wondering that.
You mean performance on downstream task or efficiency?
Downstream tasks, downstream tasks.
So the answer to that is that no, sparsity helps. Of course, if you are excessive sparsity, then after some point it's going to start hurting. But overall, across like many experiments, they help a lot. Like for example, in these results over here, where is it? Over here, things were like very sparse. I think it was like 90% or 70 or 80, I don't know. And they are much better than something that is fully dense, right? So my take on this is that there is some balance between like it being extremely sparse and being fully dense. And I think the good thing is something in the middle, right? And somehow we are at the extremes, like people do top K with a small k, which is the one extreme. In the other extreme, people do fully dense attention, full softmax attention. So we have something that is in the middle, right?
Does it change depending on application maybe, or did you did some studies on that?
On what exactly?
Like certain tasks, like do tasks need more tokens, more sparsity, maybe?
Well, not directly, but indirectly, I think that yes, some tasks requires more tokens, others not. For example, if you're doing a task like, let's say, needle in the haystack, just single needle, it's good to be more sparse, right? Because there is a single needle. But if you have more needles, then being extremely sparse starts to hurt, right? Yeah.
Maybe one last question here.
Hello again. I'm just particularly curious on these benchmarks. I'm not fully acquainted on this. So like both Ruler and Helmet are for smallish models. I know that theoretically speaking, and Max should hold for bigger models, but how much is that guaranteed? Do you really think like if you eventually like all those bottlenecks are solved and things can be scaled to, I don't know, 30 like big models and even mixture of experts and etc. What we will have the same type of results with Max, or do you think they will degrade slightly?
Degrade slightly in comparison to
these ones, yeah.
I think it will increase actually.
Okay.
As you start, the gap between Intmax and Softmax decreases because now the model has more parameters to account for the lack of, for the lack of context. But it will increase overall. Like what we saw usually is that as we increase the model size, now we are training some with 3B, 4B, is that all these results starts to increase, right? But the gap with Softmax starts to be a little bit less, but still there is a gap. There is a significant gap. In particular, some key tasks. Okay, for example, these tasks of variable tracking, common word extraction, and frequent word extraction. All experiments that we did, even with bigger models, like Intmax is always much better than Softmax on this.
Okay, thank you.
I think we're good. Thank you so much.
Thank you.